How do you transmit EM radiation from one place to another? Perhaps the most straightforward technique for this is broadcasting or beamforming. Simply send beams in all the direction from a source and it is received by the other receiver. It's easy to perform. Also, long distance transmission is possible, but it also has some disadvantages. The signal strength reduces drastically as the distance increases. The signal strength is inversely proportional to the square of the distance covered. The signal is broadcasted in all the directions, this thus wasting huge section of power and also increasing risk of stealing information. The EM waves broadcasted and countered by living beings can be hazardous to their health. Also, it is clear by now that for transmitting a large amount of power, it is not a very good way. So what do we do now? So we use waveguides. A waveguide is a structure that guides waves such as electromagnetic waves or sound with minimal loss of energy by restricting expansion to one dimension or two. Waveguide may refer to any linear structure that can convey EM waves between its endpoints. The EM waves in a waveguide discussed here can be imagined as traveling down the zigzag path being repeatedly reflected between the walls of the guide. This is a similar effect of waves of water constrained within a canal, or why guns have barrels that restrict hot gas expansion to maximize energy transfer to their bullets. Without the physical constraint of a waveguide, waves are decreasing according to the inverse square law as they expand into the three-dimensional space. There are different types of waveguides for each type of the wave. The original and the most common meaning is a hollow conductive metal pipe used to carry high-frequency radio waves, particularly microwaves. The geometry of a waveguide reflects its function. Slab waveguides confine energy in one dimension, fiber or channel waveguides in two dimensions. Due to the total reflection at the walls, waves are confined in the interior of the waveguide. In case of waveguides, a perfect electric conductor or a PEC material is used as one of the interface. A PEC is a material with negative infinite permittivity or negative permittivity of a very large magnitude, which implies that the reflective coefficient of the material is 1 and the transmission coefficient is 0, where the reflection coefficient is the ratio of the amplitude of the reflected wave to incident wave, and hence a PEC material completely reflects EM waves. Now, let's discuss the electric and magnetic fields in a waveguide. But before that, let's do a quick recap of the Maxwell's equations and its boundary conditions, which are essential for the equations of the fields. Maxwell's equations. Maxwell's equations are a set of four simple equations that describe the world of electromagnetics. These equations describe how electric and magnetic fields propagate, interact, and how they are influenced by objects. Maxwell's equations show that separated charge, positive and negative, gives rise to an electric field, and if this is varying in time as well, will give rise to a propagating electric field, further giving rise to a propagating magnetic field.
There are a bunch of different kinds of wave which we will refer to as modes in waveguides, such as transverse electric and magnetic mode TEM, transverse electric mode TE, transverse magnetic mode TM mode. TEM mode are modes in which both the electric and magnetic fields are perpendicular to each other and also to the direction of propagation. Free space plane waves is an example of TEM mode waves. Transverse electric mode or TE mode. As the name suggests, waves in which electric field is perpendicular to the direction of propagation but magnetic field is at some angle to direction of propagation, angle being not equal to 90 degree. There are TM mode waves in which waves having magnetic field perpendicular to the direction of propagation of EM wave but electric field is at some angle to direction of propagation of wave, angle being again not equal to 90 degree. What do I mean? Let's first have a look at plane waveguide. As you can see in the figure, the z direction is the direction of propagation and our waveguide is confined between planes y equal to 0 and y equal to a, both of infinite extent, and we can take electric field as shown in equation 1. By law of generality, I can take kx equal to 0. By this I mean that planes in consideration are infinite in extent and I can choose any direction I want to work on. Infinite extent ensures that all sets of direction are same in their nature. Choosing a direction such that kx equal to 0 and as we have y bounded by PEC, there will be a standing wave formation in y direction. Therefore, our equation become as shown in equation number 3 and equation number 4. To decide which of these is actually our electric field equation, we apply boundary condition. E1 parallel minus E2 parallel equal to 0. And we know E2 parallel as 0. Therefore, it comes out that E1 parallel is also 0. The second boundary condition, D1 perpendicular minus D2 perpendicular equal to sigma f. And we know D2 perpendicular is 0. but sigma f is non-zero, which implies d1 perpendicular is non-zero. Applying boundary condition at y equal to 0 and using this result, we get Ex as equation number 5 and Ey as equation number 6. Applying boundary condition at y equal to a, we get sin kya equal to 0, which means ky equal to m pi by a, where m is an integer. Now if m equal to 1, it will be called as first mode. If m equal to 2, it will be second mode, and it continues so on. Further, we know that wave number square or k square is also equal to kx square plus ky square plus kz square. Kx is 0, ky is known to us as m pi by a, and k is omega by c by definition. By using these results, we came to know that kz will be equal to under root of omega by c whole square minus m pi by a whole square. For propagation in z direction, kz is ought to be real. Therefore, m can take limited values, limiting number of modes possible in plane waveguides. Now I comment on phase velocity and group velocity. Phase velocity is angular frequency omega divided by wave number k in direction of propagation. Therefore, for a plane waveguide, Vp is equal to omega by kz, which is shown in equation number 7. It is clear as m is non-zero, therefore Vp is greater than c. Group velocity or Vg is defined as Vg equal to del omega by del kz, which comes out to be c square by Vp or phase velocity. We know Vp is greater than c, therefore Vg will be definitely less than c. Let's find out the value of kx and ky, which can be found by applying boundary conditions at x equal to a and y equal to b. Let's consider first Ex. Ex is parallel to the xz plane. By boundary condition, E1 parallel should be equal to E2 parallel. E2 parallel is known to be 0, hence E1 parallel is equal to 0. Therefore, Ex should be equal to 0 for all at y equal to 0. Hence, Ex should contain sign term with respect to y. For x equal to 0, Ex is perpendicular to yz plane. By boundary condition, D1 perpendicular is not equal to 0. Therefore, for at least some y, Ex should be non-zero for x equal to 0. Hence, Ex should have cos term with respect to x. Similarly, it can also be done for Ey. For Ez, it is parallel to both xz plane and yz plane for all x and y. Therefore, should be 0 if any x or y becomes 0. We can conclude that for Ez will have both sign terms with respect to x and y. We get sin k by b equal to 0 and sin kxa equal to 0, which implies ky can be p pi by b or kx can be q pi by a, where p and q both are integers. We also know that k square is equal to kx square plus ky square plus kz square. Kx can be put as q pi by a and ky can be put as p pi by b. We find that kz can be written as under root of omega by c square minus q square by a square pi square minus p square pi square by b square. Here Te and Tm modes are represented as TePq and TmPq, where pq represents integer discussed above, and it also means that size associated with p, that is b, is longer than a. Lowest mode is called dominant mode in both Te and Tm. Te modes have Hz, Hy and Ex, while Tm modes have Ez, Ey and Hx. In Tm mode, both p and q can't be 0, as Ez will be 0 if any p or q is 0 because of the sign terms. So, dominant Tm mode is Tm11. In Te modes, we have Ez equal to 0, while Hz should be non-zero. It is clear from the equations, both p and q can't be 0 simultaneously, but one of them can. Therefore, dominant Te mode is Te10. Now for one mode of operation of waveguide, it is to be operated between dominant mode and next higher mode. Depending upon relation between dimensions of rectangular cross section, we have different range of operations. If b is greater than a greater than b by 2, then range is c pi into 1 by a minus 1 by b. If a is less than b by 2, then the range is c pi by b. For maximizing bandwidth, generally we have a as less than equal to b by 2. But power transfers depend directly on the area of cross section. So a is chosen such that it is equal to b by 2. Hence, range is also equal to c pi by b, and we get a larger cross section area for transfer of large power.
Let's now cover the space with PC from all the sides. We get a cube called resonant cavity. A resonant cavity is a special type of resonator consisting of a closed metal structure that confines electromagnetic fields. The structure is either hollow or filled with dielectric material. The EM waves bounce back and forth between the walls of the cavity. At the cavity's resonant frequencies, they reinforce to form standing waves in the cavity. Therefore, the cavity functions similarly to an organ pipe or sound box in a musical instrument, oscillating preferentially at a series of frequencies, its resonant frequencies. Electric and magnetic energy is stored in the cavity, and the only losses are due to the finite conductivity of the cavity walls and dielectric losses of material filling the cavity. While losses from wall currents are small, cavities are frequently plated with silver to increase their electrical conductivity and reduce their losses even further. It's covered from all sides by PEC. Standing waves will be formed in all the three directions, x, y, z. So after applying boundary conditions, we find the equations to be as shown. We know that k square equals to kx square plus ky square plus kz square, where k equals to omega by c. On solving, we get omega equals to as shown in the figure.